Hey everyone, Mr. Houck here. In today's video, we're going to be looking at the graphs of the parent functions for the reciprocal trig functions secant, cosecant, and cotangent. We are also going to be identifying key characteristics of these parent functions. Let's go ahead and get started. So on our notes, notice that we have in the x column the angle in radians. In our y column, we have y equals secant of theta, or we could say, this is x, y equals secant of x. And just for time's sake, I've gone ahead and filled in our table here. So these are the secant values. One thing I've done is I've taken the exact value and I've approximated it as a decimal, just so we can have an easier time graphing this on our coordinate plane to the right. But this is the table for secant, and notice I'm going from negative pi over 2 all the way to 2 pi. This is so that we can get a nice complete picture. Okay, so let's go ahead and start graphing these values and seeing what happens when we graph the parent function for y equals secant of x, or y equals secant of theta. First thing that I want to point out here is that we have certain undefined values. And we saw with the parent function of tangent, we saw that at these undefined values, we had vertical asymptotes. And that's going to be the case here with y equals secant of theta. So let's go ahead and plot our vertical asymptotes. So we have a vertical asymptote at negative pi over 2. I'm going to represent my vertical asymptotes in red. We have one at pi over 2. And we have one at 3 pi over 2. Okay, and now let's go ahead and just start plotting some of these points here. So at negative pi over 4, we have about 1.41. So here's negative pi over 4. 1.41 would be about roughly right there. We're just estimating. At 0, we go to 1. And at pi over 4, we go to 1.414 again. And let's go ahead and sketch what this graph would look like. And we'll check in Desmos later if our graph is accurate. Okay. Next, so there's our undefined value at pi over 2, so there's our vertical asymptote. At 3 pi over 4, we have negative 1.414, so that would be about right there. At pi, we go to negative 1, and at 5 pi over 4, we go to negative 1.414 again. That one looks kind of bad. It looks a little shaky. A little better, I guess. Okay, then we have our undefined value at 3 pi over 2, so there's our vertical asymptote. 7 pi over 4, we have 1.414. It's about right there. 2 pi, we go to 1, and the cycle would continue in that fashion. And I'm going to do that. Okay, so we get an idea of what's happening here. So these are some interesting graphs, an interesting graph that we get for y equals secant of theta. And let's go ahead and talk about the period, the amplitude, asymptotes, domain, range, all that fun stuff. So for the period, we can look between the asymptotes, or not the asymptotes, we can look to see where the graph starts to repeat itself. So we have this little positive section of y equals secant of theta, then we have this negative section of y equals secant of theta, and it appears that the positive section, after the negative section of the graph, the positive section returns. So let's look at from here, 0, all the way to here at 2 pi. That's where we have one complete cycle. So let's kind of think about this here. There, there, there. And then once we get to that point, the cycle would start to repeat itself. That's one way we can look at the period. So the period would be 2 pi. An easier way maybe to look at it is just to look at this positive section, which would start at negative pi over 2. This negative section, which would end at 3 pi over 2. And the distance from negative pi over 2 to 3 pi over 2, that would also be 2 pi. I know that some students kind of like to start at 0 just so the period is easy to calculate, but going from negative pi over 2 to 3 pi over 2, this is also one complete cycle, and that period is 2 pi. So our period is 2 pi. Our amplitude, well, remember the amplitude is determined by maximum minimum values. There is no amplitude here. No amplitude for secant. And the asymptotes, well, we already noticed that we have an asymptote at negative pi over 2, positive pi over 2, 3 pi over 2. The next one would be at 5 pi over 2. So it's looking like odd multiples of pi over 2. Let's go ahead and record that. These are odd multiples of pi over 2. And that would be, again, negative pi over 2, positive pi over 2, 3 pi over 2, 5 pi over 2, and so on. Okay? So the domain, if we think about the domain here, all real numbers are possible except for values that are asymptotes. So I'm going to say all real numbers except at asymptotes. And when we think about the range, so the range is the possible y values that the function takes up. Well, notice that between -1 and +1, there's nothing. So the way that we would say this is part of the range goes from -∞ to -1. I'm going to put a bracket on -1 because we do have a value there. So -1 is included in the range. Union +1 to infinity. So again, there are values at -1, and then they continue upwards towards infinity. So let's go ahead and compare this graph with the graph of y equals secant of theta that we'll get from Desmos. And let's look for some key points here. So in Desmos, we are getting the point 0, 1. We can see that right here. We can see that let's go and take that off here. So if we zoom in, there we go. We can see halfway between 0 and pi, this would be pi over 2. We can see a pi over 2. We have this asymptote here. We can see a pi. We go down to -1. So our values are looking correct. And we can see that in each direction towards -infinity and +infinity on the x-axis, this graph is repeating itself. So we have a periodic function. So next, we want to graph y equals cosine of x on the same graph and see what we notice. And I'm going to do this in a different color. I'm going to use blue. All right. So we know that for cosine, well, cosine starts at 0, 1. By the time it hits pi over 2, it's at 0. By the time it hits pi, it's at -1. Then 3 pi over 2 goes to 0. 2 pi is back at +1. And negative pi over 2, we would have 0 as well. So let's go ahead and draw our curve. I think I can do better than that. Not bad. Okay, so let's see what we notice here. Let's talk about some things that I notice. The first thing I notice is that the maximum value for y equals cosine of x turn out to be the minimum values for the positive section for y equals secant of x, or secant of theta. Another thing that I'm noticing is that everywhere that there is an x-intercept for y equals cosine, it also corresponds to an asymptote for secant. And you might be wondering, why did we choose to graph y equals cosine of x? Well, remember that the relationship between secant and cosine is that they're reciprocals of each other. Secant is the reciprocal of cosine, and cosine is the reciprocal of secant. So they already share that relationship with each other. And we can see from the graph that, very interesting. So those are some of the things we want to record here. The maximum values of the cosine function are the minimums for the positive sections of secant. So again, maximum values for cosine are the minimums for the positive sections of the secant function. And same thing, minimum values for cosine are maximum values for the negative sections of secant. And then, of course, again, the x-intercepts for cosine are also the locations of the asymptotes for secant. So pretty cool. All right, let's take a look and see what would happen if we now look at cosecant. So once again, I've gone ahead and made the table for y equals cosecant of theta or y equals cosecant of x. And let's go ahead and plot these points. So once again, I'm going to start with the asymptotes. We have undefined values at 0, so let's put an asymptote at 0. We have an undefined value at pi. And we have an undefined value at 2 pi. So it's looking like every integer multiple of pi, 1 pi, 2 pi, 3 pi, 4 pi, and on, we're going to have an asymptote. Same thing in the negative direction. Now let's go ahead and plot our points. So at negative pi over 2, we go down to negative 1. At negative pi over 4, we're at about negative 1.4, so that's roughly right there. Let's go ahead and draw in what we would get. At pi over 4, we have about 1.4. At pi over 2, we have positive 1. And at 3 pi over 4, we have about 1.4 again. Okay, at 5 pi over 4, we have negative 1.4. 3 pi over 2, negative 1. And 7 pi over 4, about negative 1.4 again. So we can see the graph of y equals cosecant of x looks very similar to the graph of y equals secant of x, but shifted, horizontally shifted. And we can see that because here the asymptotes are 0, pi, 2 pi, whereas when we were looking at y equals secant of x, the asymptotes were at negative pi over 2, pi over 2, 3 pi over 2, and so on. But the shape of the graph is the same. So let's talk about period here as well. So once again, let's look for one complete cycle. If I start here at 0, here's the positive section of y equals cosecant. Here's the negative section of y equals cosecant. And by the time we hit 2 pi, that positive section will be repeating itself. So from 0 to 2 pi, we have one complete cycle of the graph. So the period would be 2 pi. Okay. The amplitude, once again, amplitude is based off of distance from a midline to a maximum or distance from a midline to a minimum. We don't have any minimums or maximums because the graph of secant and cosecant go infinitely in the y direction for both positive and negative infinity. So there is no amplitude. And the asymptotes, as we just noted a moment ago, look like they're occurring at every integer multiple of pi. So I'm going to call this integer multiples of pi. Okay, so again, that would be like negative 2 pi, negative pi, 0, 1 pi, 2 pi, 3 pi, and onward. Okay. So when we think about the domain, very similar to the secant graph that we just saw, the domain is going to be all real numbers except for where we have asymptotes. So all real numbers except at asymptotes. Okay, and the range, again, very similar to the secant graph. We notice that from between the values of -1 and +1, we don't have anything. We don't have any y values. So the range is going to be negative infinity to -1, union 1 to infinity. All right. So similar to how we graphed cosine on the secant function, let's go ahead and graph sine on the cosecant function since sine is cosecant's reciprocal. And I'm going to do this in green here. So I know that sine starts at 0, 0. By the time we hit pi over 2, we're at 1. By the time we hit pi, we're at 0. 3 pi over 2, we're at -1. 2 pi, we're at 0. And let's just continue the pattern over here. Negative pi over 2, we're at -1. Okay, so there is an attempt at a curve there, and let's see what we can notice here. So very similar to secant and cosine, notice that the maximum value or maximum values for sine are resulting in minimum values for the positive sections of cosecant, minimum values for sine are resulting in maximum values for the negative sections of cosecant. And we can also see, just like with the secant and cosine, we can also see that the x-intercepts for sine are the asymptotes for cosecant. So they share that similar relationship as we saw in the previous graphs. Okay. So there's our relationships. You can take a moment to pause and write those down if you need to. And one thing we want to be able to do is distinguish between the parent functions and the graphs for cosecant and secant. And one way that I like to do that is through the asymptotes. So if we're looking at the parent function here for cosecant, we can see that the asymptotes run at integer multiples of pi. If we were looking at the parent function for secant, we saw that the asymptotes are running negative pi over 2, pi over 2, 3 pi over 2, so odd multiples of pi over 2 instead. Okay. Now let's go ahead and take a look at tangent, or sorry, cotangent rather. All right, so again, here's our table for y equals cotangent of x or cotangent of theta. And let's go ahead and take these values and graph them on the coordinate plane provided. So let's use purple here. And once again, just like with secant and cosecant, we see these undefined values. We understand that these are going to result in vertical asymptotes. So we're going to have vertical asymptotes as 0, pi, 2 pi. And if we continued that pattern, we'd have one at 3 pi, 4 pi, 5 pi, every integer multiple of pi. Okay. Now let's start putting in some of these values. So at negative pi over 2, we were at 0. At negative pi over 4, we were at negative 1. And here's what the graph would end up looking like. Okay. At positive pi over 4, we're at positive 1. At pi over 2, we're at 0. At 3 pi over 4, we're at negative 1. At 5 pi over 4, we're at 1. At 3 pi over 2, we're at 0. At 7 pi over 4, we're at negative 1. And this pattern will just continue to repeat itself. Now let's think about what this looks like compared to the normal function of tangent. So let's hop over to Desmos for just a moment. And let's see here. Let's look at tangent when compared to cotangent. So if you look at the graph of tangent and you look at the graph of cotangent, it looks like they're almost facing opposite directions. You can, and I use the word facing kind of loosely here. You see the way that this is curved like that? Well, it looks like tangent is curved like that. So they almost, again, facing opposite directions of sorts. So let's talk about some of these key features of the cotangent parent function. So first we're going to start with the period. Well, if we look here, one complete cycle is happening from asymptote to asymptote. So from 0 to pi, we have the full cycle of the cotangent curve, and that's repeating every pi units. So the period here, just like tangent, the period is pi. If we think about the amplitude, well, remember amplitude talking about from midline to maximum or midline to minimum. Since these cotangent curves are extending infinitely in each direction on the y-axis or in the y direction, there is no amplitude. We don't have any minimums or maximums. And asymptotes, well, we can see the asymptotes are happening at every integer multiple of pi, 1 pi, 2 pi, 3 pi, and so on. So we'll say that's integer multiples of pi. Okay. The domain is all real numbers except for at the asymptotes. And the range, we can see here that the entire y-axis of values is being used, so the range is from negative to positive infinity, or all real numbers for the y-axis. Now, very similar to the other ones, let's see what happens when we graph y equals tangent of x, since cotangent and tangent are reciprocals of each other. So I know that at y equals tangent of x, at negative pi over 4, we're at negative 1. At 0, we're at 0. And at pi over 4, we're at positive 1. I know that at 3 pi over 4, we're at negative 1. At pi, we're at 0. At 5 pi over 4, we are at positive 1. 7 pi over 4, we're at negative 1. 2 pi over 0, so on and so forth. Okay. In an effort not to clutter up the graph, I'm not going to draw in the asymptotes for tangent, but we can see where the asymptotes are. We can see that the asymptotes would be here at negative pi over 2, here at, where was I? Hold on. Here at pi over 2, negative pi over 2. We would have one at 3 pi over 2, and so on. So let's talk about some things that we notice. The first thing that I notice is that the x-intercepts of tangent, so right here, tangents in pink, the x-intercepts of tangent are the asymptotes for cotangent, right? X-intercepts of tangent are the asymptotes for cotangent. That's one thing I notice. Also, the asymptotes of tangent are the x-intercepts for cotangent. So everywhere we see an x-intercept for cotangent, that's where the asymptotes for tangent would be. As we already mentioned, the graphs face in opposite directions of each other. And another thing that's interesting here is that tangent and cotangent are equal to each other at odd multiples of pi over 4. So at negative pi over 4, we see the two graphs intersect. At positive pi over 4, the two graphs intersect. 3 pi over 4, they intersect. 5 pi over 4, 7 pi over 4. So we can see the intersection of the reciprocal functions at odd multiples of pi over 4. Okay? If you need to, take a moment to pause that. But those are the graphs of our parent functions for our reciprocal trig functions, secant, cosecant, and cotangent.